Okay, thank you very much. Thanks to KX for letting us come and talk here today. My name is Jonny Press. I work for Data Intellect. So we're partners, obviously, of KDB. We've been kind of in this community for about 15 years or so now. So what I want to talk about, a couple of things today about KDB-X, and I don't want to go over too much more of what, just repetition of what Connor talked about, but I'd like to give a little bit of our view. So we're very excited by it. We like the impetus, we like the direction, we like the renewed focus on the core product. We are builders and engineers at heart, and this plays to our strengths. So we really like that. We are less keen on the use of uppercase, but we can probably just about get over that. So in terms of what we like, okay, Parquet integration, that's going to bring KDB into the open data ecosystem. It's going to bring more data to KDB use cases, and it's going to bring KDB data to other use cases. That combined with virtual tables, I think that's going to present us with a very interesting engineering challenge about how we can optimize existing setups. Gives us a lot more optionality in terms of data structuring from a long-term point of view. That's exciting, right? New stuff to play with. The AI piece, again, a lot of the AI use cases are becoming real. We were in with a client today, literally talking about how they could bring AI into their pricing workflow. And we're going to see more and more of that. The dual mode capability that KDB-X is going to bring with the structured and unstructured data, it's going to open up a lot. And the MCP server, so KX released an MCP server a few weeks ago. We've downloaded that, been playing around with it. It's a nice piece of kit. It's extensible, allows natural language integration with KDB data sets. We had actually tried building something internally, and we think that we need to throw that away now because that one looks better. But anyway, that's how it rolls. GPU acceleration, I know Nataraj is going to talk about that, but again, we're performance oriented. So anything that improves the performance of a system, that's exciting to us. Any more capability on specialized hardware, that it's just going to bring more to the community. The last thing is modules. So we've been working with KX and trying to seed this module environment. We're building on GitHub. We released those last week or the week before, so we've kind of been cobbling away in the background. So what does this mean? So we would love it if between ourselves we could build a strong foundation, which was the basis of most KDB systems. So there's a lot of, we all spend a lot of time building components that are also being built elsewhere, and they're very, very similar. And obviously, developers have opinions. There's not one size fits all, but there's probably one size fits 80% for a lot of it. So we would like a foundation where somebody who's building a new system has a strong starting point, or somebody coming new to the environment can just leverage a lot of work that other people have done. So we've made a start. Again, what we tried to do there was take some of the components of Torque and turn them into the modularized base. But we'd be very interested in feedback. So there's a QR code that takes us to our GitHub site. We've got kind of a voting system on there as well. So, we've sort of outlined some of the things we're thinking about building. Be interested to hear feedback, what lands with people, what doesn't land with people, or suggestions as well, because we're open to that too. And the next thing, so the other thing we've done, so we released this today. So we've put together a white paper. Again, you can download it from the QR code link. This is focused on building real-time event-driven systems in KDB. So it leverages a lot. There's a lot of new material here. It leverages some of the work we've published previously, but it's very much focused on those real-time use cases. So it's not about long-term historic data storage, super complex long-range analytics or anything about that. It's about those problems that people have whenever they're trying to get data from one end of the system to the other as quickly as possible. And it's kind of it comes at it from two angles. It comes at it from a top-down design point of view, but also from a bottom-up individual performance characteristics, right? So what are the little operations that really actually accumulate up to impact the performance of a real-time system? So we're quite proud of it, to be honest. I think it's we're going to have missed stuff. Again, we'd love some feedback, right? If there's bits that people want to ask us to add or say we've got completely wrong, we'd love to hear that feedback. We want to make this a living document. So as KDB-X, as the functionality of KDB-X grows, we want to kind of feed that into this document and have it as a decent reference for anybody who's building this type of system. So what I want to talk about is, again, could have done a diagram, right? There's architecture pieces in the document, so box diagram, done some hand waving. I've also gone with QStudio in honor of Ryan, who's not with us. He's not dead, he's just not here. Okay, so I've preloaded some of this stuff because I can't use two hands on this, right? So what we're talking about here, so this is just an example from one of the things we talk about in the white paper. So a specific example, so what I want to talk about is data structuring, okay? So, because there's things, whenever you choose how to structure data in a table in KDB, those choices kind of feed the whole way through and they've got an impact the whole way through the system. So I want to talk about a little bit of order book analytics that we can do, and two different ways that you could think about structuring the data and the impact that has on the analytics that you want to do, the memory that the system requires, and some of the IPC overheads associated with that. So this kind of initial choice feeds right through the system. So again, the white paper we have tries to basically give you ways to create data sets, example little data sets that you can kind of experiment with yourself in your own time on your own hardware. So this example, so what we're concerned about here is not working. It's not working. Right, hold on. That's not the right one. There we go. Okay, so if we're thinking about an order book data set, so this table in here is 100,000 rows. I'm showing the first five of it, first 5 rows. So basically, when we talk about order book data, we are, obviously when you're trading in a market, you've got the best price, but then you've got all the other prices and orders that sit behind that. And how do you structure that data in a KDB database? And what we tend to find is that there's two ways that people do it. So one of them is using a nested structure like this. So we've got nested lists. So we've got one list of prices, one list of sizes, and they can be of any length. So the nice thing about this is it's very, very flexible, as you can store however many levels of the order book that you like in this structure. But for a lot of analytics, when you get kind of deeper into the order book, the prices have less and less relevance. So for a lot of types of analytics that you'd want to do, you maybe only need 5 or 10 levels. So if you don't need all the levels, then you can be a bit more. You can think about what you can throw away, and instead of going for this nested structure, you can go for an individual column structure. Okay, so instead of one nested list, we've got 3 individual columns for each of the prices and the sizes. So say we want to do a little analytic, and the analytic we want to do is, given an order of size X, whatever this is, but let's say 1,000, what price do we achieve whenever we trade through the book? So what's the volume weighted average price as we trade through the book? So if you look at that first row of the table, if we're trying to trade 1,000, a size of 1,000, the first size we see is 686. So we've got to take that whole price, we've got to take all the volume at that price, and then we've got to take some of the volume at the next price. Okay, and we've got to keep going through the book like that until we trade as much as we need, as much as we want. So this is the analytic, right? So this is what the bit of code looks like that we've created to do that. So it's a vectorized operation, and I think it's worth. I think the other thing is it's great KX extending the extending KDB so it supports its full SQL support, full Python support. That's going to bring more people to the community. It's going to enable AI use cases, but it's also nice to appreciate Q, right? You know, the combination of a time series database with a vector programming language that understands order is a match made in heaven, right? So whenever you want to do analytics like this, you know, you can write neat little bits of Q code to do it. I also asked Claude to generate me the equivalent SQL, and that made me sad. Sadder than the uppercase thing, but it's so this is what the Q code looks like. So let's have a look and see what the performance. So if we just run that bit of Q code, so what you see on the end here, we've added a column called VWAP price on the nested structure, which in the first row 71.414 seems about right. We're taking most of the 71.1 and some of the 72.1. Sounds about right. Let's assume the maths is correct. So performance-wise, what does that look like? So the problem when you have a nested structure is it can be ragged. Okay, so you can't vectorize in the same way that you can when you're dealing with columns. So what you have to do is you basically have to iterate. So the same bit of code, the same fill price for size. So it's still a vectorized operation because it's working on the nested lists, but it has to work through the rows of the table. So if we put a timer on that, we can see that's 150 milliseconds. Let's just run it a couple of times in case there's something weird going on, but sort of 150-ish. But whenever we have it split into columns, we can vectorize down the column as well, so we can actually vectorize the whole operation. So if we run that in comparison, I'll run that a couple of times. So let's ignore the first one. So the second time around, we get 4. So I don't know what that is, like somebody better at maths than me, 30, 40 times speed up. So it's 30 or 40 times quicker for the columnar version of this table. So we've been able to make the choice that we didn't need the extra prices. So let's just check these two things are equivalent, just to make sure I'm not cheating anybody, which they are. So then, okay, so that's good. Analytics are better. What about memory usage? Again, so memory usage, you know, it's not immediately obvious in Q how much memory an object uses. So, you know, one of the things we had in Torque, which we've now turned into a package, is this memory usage module. So this has got a couple of little utilities in it for helping us calculate the memory usage used in a process. So if we so we've loaded in our module, and we look at what the output is. So we've got this little mem usage all function. So this is basically the memory usage of an object as reported by -22. So -22 is the serialized size on the wire, but this is not the actual memory usage of the object. This is how much memory it would use, or how, the space that it takes if it's for the serialized size. But we can see the nested object's a little bit bigger. It's 5 megabytes versus 4 megabytes. So another function we have in our memory usage package is this object size one, which actually goes and tries to do the calculation, the actual real calculation. It has to sample the data set some of the times and make some assumptions, because otherwise it would be far too expensive. But it gives you a much more accurate representation of what the real size in memory is. So if we just run that one, so our wide format is again about 5 megabytes, so it's telling us this is actually 5 rather than 4, but nested one is about 12. And this is a slightly skewed example. There's a bigger impact here, but really so the nested object here is taking more than twice the memory of the columnar format. This is a slightly skewed example, but generally those nested objects will be more expensive memory-wise. Okay, so what about if we're shipping over IPC? Whenever we think about real-time systems, we got to ship a lot of data around. We got to transfer it over IPC, because that's the whole thing. It's event-driven. You're putting data from one process to another. So We can test that out as well. And again, there's a lovely thing about KDB. You can isolate the work that it's doing. You can test it and you can work it out. So we open a connection to a remote process, and then let's just see how long it takes. So I'm just going to make a synchronous call with the two objects 10 times from here to the other process, and I'll run these both a couple of times. So with the wide format, it's about 22. This is for 10 iterations, so about 2 milliseconds to ship it. With the nested format, it's 170, so 17, 18. So it's much more expensive to also ship this in memory or ship this object between processes as well. And why is that? Is it the difference in the size? Well, the answer is no, it's not really the difference in the size. The difference is in the serialization, the deserialization. And again, we can again isolate those components. So, if we serialize 10 times and then deserialize and reserialize, we can see the timings for those. And we'll see with the nested structure, if we just skip straight to the end, most of the time is not on the shipping the data. It's the deserialization, the reserialization, which is all kind of CPU bound. So yeah, that's my conclusion. So have a look at the white paper. It's got a lot of little examples like this. It's top-down approach, but also kind of bottom-up approach. And that's me. Thank you very much.